This part is about significant figures, multiplication, and division. I wasn't able to squeeze it in the last recording, so here is it separate. So here it says your answer must contain no more digits total than the number with the least number of digits total. So you look at the three numbers on the left, and they have each no, that's not true. The first one has 3 significant figures, and the other two have 4 significant figures. So the answer must have 3 significant figures, and I'll show that in just a moment. Notice on the 5.10 that 0 is significant. That number was measured to 5.10. It's not 5.09, it's not 5.12, it is truly measured to 5.10. So that 0 is significant. As I said earlier, the ones that are not significant are, the zeros that are not significant are the trailing zeros on whole numbers. So here I'm on the graphing calculator. I'm going to type in 5.10 times, or could be any kind of graphing, could be any kind of calculator, times that number times 5.425, and there we go, 171.92585.845. 9 digits are shown. It's an overkill. It's ludicrous to write down the entire number here. We have to truncate it somewhere, and it makes sense to use a certain rule. Well, use the rule by the least number of digits, which is 3. So you round it to 172. Notice what happens if one of the numbers that we just used is changed in the very end. Notice, it's still 172, isn't it? But look at the garbage in the back. The 575364 versus the 25845. I mean, completely different. And we just changed a little bit in the back. I do it again. I'm going to change. Hold on. I'm going to change this number over here, 6.215. And gosh, it's still 172. So why write down all the stuff in the back? The 85209 has already changed dramatically, but the stuff in the front, the stuff that is significant, has not changed. It's still 172 when we change that last number, last digit on one of the numbers. Same for division. 205.244 divided by 2.7 is 76.016. 2 significant figures according to the 2.7, therefore the answer is 76. By the way, in the last couple of problems, that's a coincidence that we come up with integers. It just so happens that this particular problem here with 2 significant figures, 76 also has 2 digits. This is about significant figures and the rules that are used for addition and subtraction. All the digits that are written down for a particular number are significant with just one exception. And I'm going to get to that exception soon. It will be about trailing zeros. Not just yet. Look at the number 104.075. That number is accurate to 6 significant figures. That includes the zeros in between there, and they're not just there, but they need to be there. They're placeholders. If you leave it out, it's a different number. So that 0 there is significant as well. Now you add these numbers here and you come up with something, and your calculator will say 314.9602, but that needs to be rounded. And as you read through this here, apparently to the least number of digits after the decimal point, which is indicated by that 1 and the 1.1. Why? Well, because that 1.1 was only measured to 1 digit after the decimal point. So it doesn't matter that on the other two numbers you have 852 there and 75. Those numbers, once you have added them, need to be rounded for the 314.9602 to just one significant figure behind the decimal point. And so we come up with 315.0. Now that 0 there needs to be written down as well, because if you leave it out, it looks like a rounded 315. It's not. It's exactly 315.0. It's not 315.1. It's not 314.9. It's 315.0. It could be 315 15.03 rounded down, but still that 0.0 there indicates that's how accurate you measured. Similar on this one, and you see how the numbers came about. Least number of digits behind the decimal point, which is 2, and therefore 2 of these survive. Okay, here we in fact have trailing zeros. Look especially at the 2,400. Is that an exact number? Well, it's very likely that it's rounded to the closest 100. How do we know that? Actually, we don't. What is happening is that we would have to look at the context. So if it says, well, we measured about 2,400 grams. Well, the word about is in there, and then you know that it's rounded to the closest 100. And that's what you go by. So you add these numbers, and obviously you're going to come up with 2354, and that needs to be rounded then to the closest 100. So here, these trailing zeros, I call them, are not significant. They're still placeholders, but they're not significant as if there was a 0 in the middle or a 0 being behind the decimal point and being the last one. What about the other one? The result on the calculator is 35,839, but as you see, the trailing 0 on the 870 and on the 34,650, which means it needs to be rounded to the closest 10, so the answer is 35,840. And that's what you see here, 35,840. Significant figures, what happens to the zeros? I will show this in 3 different ways, one building on the other. First, a very quick overview, then a justification for what I did, and then example problems. So let's get started. Here are 6 such examples. 82, both are significant. 0.1659, these 4 are significant. 1.08, these 3 are significant. 0.00142, those 3 are significant. 2.00, those 3 are significant. On the 94,000, that looks like the 94 is significant. On the 100, that looks rounded, so the 1 is significant. And on the 40, it looks rounded, so the 4 is significant. I will actually comment on this last example later on. Very quickly, of course, this one here is both of them are significant. There aren't any zeros in here. If you look at the next 3 here, then you see that anything where we have leading zeros, these are not significant. I try to get these 3 in here. Anything where you have zeros behind the decimal point, those are significant. So again, leading zeros are never significant. Trailing zeros become significant if they are behind the decimal point. Sandwich zeros are also significant. Trailing zeros in front of the decimal point, in this case actually there is none, that's a little bit ambiguous, and that's where I'm going to talk about later. Okay, here comes the justification. For the first one, of course these are non-zero digits anyway. On the second one, notice that the 0 here is not necessary. We can write it like this, and we often do. However, I do prefer to write a 0 there, even though it's not necessary, because of this one. It makes the number look nicer because a lone decimal point may be overlooked. So at the 0.1659, if you write that down very quickly, you could accidentally do this. That doesn't look much different. But if you make sure that you have the 0 in front of that, then you know exactly that this one is a 0.1659. In any case, it's a leading 0 and it's not significant. Okay, next one. In this case, the 0 is necessary. because if it wasn't there, this would look completely different, so it has to be there. It's also significant because it's sandwiched between non-zero digits. On the next one, of course, the two zeros behind the decimal, these two here, are necessary. The first one is actually not, but again for the same reason of or not overlooking the decimal point, I like to write it there. But these two here are not significant. Any leading zeros are not significant, and these three, of course, are non-zero digits, so they are significant, of course. The next one. Why the trailing zeros are significant? Well, first of all, in order to write down just a 2, the 0.00 is not necessary, because 2 equals 2.00. However, since they are written down, this is what must have happened. This must be a measurement or computed result, and the zeros are significant because otherwise they wouldn't have been written down. Perhaps a computed result of 2.0039 was rounded to 3 significant figures. In order to show that the result is that accurate, those two are written here to show that there are 3 significant figures. So you did measure or compute it that accurately. It's not just a 2. That would only indicate it's 1 significant figure. You measured more accurately than that, 2.00. And I show the last one in my next recording. And here's the last case, 94,140. And I said something about that. Well, first of all, these zeros are necessary, because otherwise the numbers wouldn't look like a 100 if I left one out. But are they significant? It's hard to tell. We need to know the context. Trailing zeros in front of the decimal point, when there's no decimal point written, are ambiguous, and I'll explain it later in an example. The 5 cases that we looked at before, the 5 examples we looked at, it was clear-cut. Sandwich zeros are always significant. Trailing zeros behind the decimal point are always significant. Leading zeros, no matter what, are never significant. Okay, let's look at the first example. How many protons does lead have in its nucleus? From a periodic table we find that lead has 82 protons. That's clear-cut. There aren't any zeros involved in any case. The second example I got from Convert. 165.9 milliliters to liters. Notice there are 4 significant figures. So whatever I convert here has to have 4 significant figures. In fact, it does. 0.1659 liters. The leading zero here is not significant. I could even leave it out and write it like that, but I said I like to write it there so as to not overlook that decimal point there. Okay, next example is 11.6 milliliters of cola drink has a mass of 12.5 grams. Determine the density. Dividing the two numbers yields 1.08 grams per milliliter. Well, the two numbers I start out with, I have 3 significant figures each. That means that the result also have to have 3 significant figures, including that sandwiched 0. That's a justification for it being significant. This one here says vitamin C tablet has a mass of 0.250 grams. The 0 here in front is neither necessary nor is it significant, but again I like to write it down so as not to overlook that point there, that decimal point. This 0 here is significant. Watch what happens if I take it away. Well, 0.25 looks like 0.250, but this would indicate that I measured the mass only to 2 significant figures. I didn't do that. I measured it to 3 significant figures. I didn't measure 0.249 grams or 0.252 grams. I truly measured 0.250 grams. So what I measured here is accurate to 3 significant figures. Okay, the molecular mass for vitamin C can be calculated from the periodic table as 176.14 grams per mole. Determine the number of moles present. We do that by dividing the two numbers, and the result has to have the least amount of significant figures. Our top number here has 0.2503 significant figures, and 5 significant figures down here gives 3 significant figures, the 142. The leading zeros here, of course, are not significant. The next example A sample of oxygen gas has all these numbers attached to it, volume and pressure and a temperature. Then the gas is heated to a certain temperature and a certain pressure, determine its new volume. This would be the calculation. All these numbers involved here have three significant figures. That means the result also has to have three significant figures. When you plug that into a calculator, you come up with 2.0039 and some other junk behind it. Well, you have to round it to three significant figures, and that happens to be 2.00. Notice that those trailing zeros behind the decimal point are significant. If you don't write them down, you'd be writing down just a 2, and you're pretending that you're as accurate as just one significant figure. You're not. You're accurate as three significant figures, so you have to write down 2.00. Okay, the last one is the case where we have trailing zeros in front of the decimal point without the decimal point written down. The first number I got from, well, there are 94,000 members of the American Chemical Society employed in 2000. Well, that sure looks like a rounded number. As I said, you get that from the context. At this point, I'm actually running out of time for my recording, so I'll be doing the last two numbers here in the next recording. Okay, this is where I had stopped. I said the 94,000, I got that from the context of that how so many people are employed. And it sure looks like a rounded number, therefore two significant figures. Okay, the next one I got from the following. The element thulium with atomic mass 69 has an atomic number 69 has an atomic mass of 168.93. Determine the number of neutrons in a typical thulium atom. Thulium-169 is the only stable isotope, and it makes up 100.0% of all thulium found on Earth. Okay, notice that the 169 here also means the number of protons and neutrons in the nucleus, and that's really, really close to the atomic mass. Okay, so what I do is here I calculate 169 protons and neutrons minus 69 protons, and I come up with 100 neutrons. Because it said start out with 169, subtract 69, and I come up with exactly 100 neutrons, not with 99, not with 102. I come up with exactly 100 neutrons. All three are significant. However, I didn't know that. By just presenting that number earlier, just 100 sure looked like a rounded number. But it turns out from the context that no, all three are significant. It's sometimes hard to signify that. Perhaps put a little bar on above the last significant zero. I underlined all three in this case. Okay, and the last example. Convert 104 degrees Fahrenheit to Celsius. This is the formula, and when you plug that into the calculator, you come up with 40. That's all it's going to give you. But notice we start out here with three significant figures, and then we subtract two significant figures, and then we multiply with an exact number of 5/9. And then we have to round to the last significant figure here because we're doing a subtraction, and so we come up with 40. It's not 41, it's not 39, it truly is 42 significant figures. Again, that comes from the context. If it had come out to 41 degrees Celsius, we would have actually to start out with 106 Fahrenheit, which is different. And if we had started out with 102 Fahrenheit, we would have come up with 39 degrees Celsius. But we happen to have 104 Fahrenheit, and that truly is 40 degrees Celsius, not even rounded. Two significant figures.